So we'll define a function pi of m. So here pi doesn't mean 3.14. It's a function. This is just the number of primes less than or equal to m. So m here, in this case, m is actually any real number. It could be any real number. And this is the number of prime numbers up to m and including m. So p of 3 is 2, because 2 and 3. Sorry, pi of 3 is 2. Pi of 4 is also 2, because you're still only counting 2 and 3. Pi of 10 is 4, because you've got 2, 3, 5, and 7. 4 primes up to 10. Okay. So I give a prime number theorem. Well, it's in the homework, so I'll leave it. Well, I'll say what the prime number theorem is. The prime number theorem to me is just one of these amazing theorems that the primes seem to be irregularly spaced. They don't seem to follow any regular patterns. But here's something we know. If you take pi of x divided by ln of x, well, this is what? This is pi of x ln of x divided by x. If you take the limit of this, as x goes to infinity, it's limited, tends to 1. This tells you roughly what the density of the prime numbers are as you go out in bigger and bigger x. About how many primes there are up to very large x. It's roughly, the number of primes up to x is roughly equal to this, x divided by the natural log of x. Right. This is just amazing to me how anyone could prove this, but this was proved well over 100 years ago. Right. So that's known, but this doesn't. This just tells you what the limit is. It doesn't tell you. It doesn't actually allow you to compute pi of x exactly this way. You just know that it tends to this limit. All right, so that's the prime number theorem. So let's find all the primes up to some number m. Another classical method called, anyone want to dare to pronounce this?
Aristophanes.
Pretty close. It's the sieve of Eratosthenes. Okay. The sieve of Eratosthenes. Finding all primes less than or equal to m. Here's what you do. You start with all the numbers from 2 to m. Write them all out. And then what you're going to do is you're going to cross off numbers that you know are not prime. So the way you do that is you're going to repeat this until the list is empty. Declare the first number on the list to be prime. So that's going to be 2. Cross out all its multiples other than itself. And then consider the rest of the list. And then repeat this. Declare the next number on the next smallest number on the list to be prime. And keep going until all the numbers on the list are either crossed off or they've been declared to be prime. Okay. And the prime that you declare on the nth repetition of this is going to be the nth prime in increasing order. So you can get all the primes in increasing order this way. So let's do a quick example. And so the numbers declared primes are precisely all the primes less than or equal to m. So let's do this. Let's do this kind of systematically. I'll do a two-dimensional table. So these are the ones digit, and these are the tens digit. Go up to 80, I guess. Okay, so this is going to be Well, I don't need those. I'll probably put in rows here. That would be useful. Yeah, I'll put columns in too. Yeah, mine will go to 100. Or at least up to 99. Okay. So, for example, this is going to be what number? 25. All right. So, 2 is not prime. That's not on the list. 0 is not prime. 1 is not prime. The list starts at 2. So, n here is 99. So we declare the smallest number on the list to be prime. So I'll represent that by a circle. And then we cross off all the multiples of 2 that are higher, because we know they're not prime because they're divisible by 2. So those are all the even numbers except for 2. So that's going to be all of these, all of these, all of those, all of those, and all of those. Okay? So every other number. Now go back, and are there still numbers on the list that haven't been declared yet? Take the smallest one, declare that to be prime. That's 3. Now cross off all the multiples of 3 that are still on the list. So the even multiples of 3 are already crossed off. So I only care about the odd multiples. So what's the first one? 9, and then 15, and then 21, and then 25, 24, 27. Okay. 33, 39. Notice a pattern here. These x's are going down like this, and these x's are going down like that. That repeats. But 51. Did I miss one? 51 is next one. Okay. And the next one is 75. And then the next one is 81. Okay. Good. So what's the next prime? 5. Now we cross off all multiples of 5 that are still on the list. And these are going to have ones digit, either 5 or 0.
Got it.
Zeros have already been crossed off. So what's the first number I cross off? It starts with 25. Okay, what's the next number that's still on the list? 7. Now I cross off multiples of 7. What's the first number I cross off? 49. So 49 goes. So that's there. What's next? 6, 3, 70, 77, 84, no. What's next? 91. And 98's already gone. That's it. That wasn't many. That wasn't much. All right. What's next? 11.
22.
What's the next number I cross off?
33. None. They're all crossed off already.
They're all crossed off already. Yeah. So 11, 22, 33, 44, 50. You're just going down the diagonal, right? They're all crossed off. There's a good reason for that. Let's go back to 2. What was the first number we crossed off on behalf of 2? It was 4. 3. What was the first number we crossed off on behalf of 3? 9. 5. What was the first number we crossed off because of 5? 25. You see a pattern there?
Squares.
Yeah, 25 is 5 squared. 9 is 3 squared, and 4 is 2 squared. What was the first number we crossed off for 7? 49, which is 7 squared. Why do we... So we claim that we could start right with the square of the number, and we don't have to worry about anything less than the square of the number. It's already crossed off. Why is that? Like for 7, for example.
You multiply it by 6 by lesser prime already. It would already be done.
Yeah, if you're right. If you're less than 7 squared, you're going to be 7 times a smaller number, but you've already crossed, so you're going to be a multiple of a smaller number, a smaller prime number, and so you've already crossed that off. So the first number you're going to cross off is going to be 7 times 7. Because 7 times anything less, you've already crossed it off because of that thing that's less. Okay. So once we get to 11, 11 squared is 21. That's already off the list. So in fact, every single thing that we haven't crossed off yet is prime. So 23, 20, 29. Okay. All of these.
That was stupid. That was stupid.
All of these are prime. All right. Good. So once you get past the square root of m, once you get past the square root of m here, then you can just stop, and everything else on the list is going to be prime. Okay, you don't have to cross off anything else. All right. Questions? All right. Good. So, well, we found all the primes, in fact, less than 100. So that's certainly. So what is pi of 50?
15.
15. So you're just counting the circles up through 50, and you get 15. Okay, fair enough. I'll buy that. What is p of pi of 50?
What's p?
No, okay. The animation isn't even given to me yet. What's p of pi of 50? So this is 15.
Seven? How do we do that?
So pi of 50 is 15. So p of 15, what's the 15th prime?
47.
It's 47. Okay? So notice that 47 is the largest prime that does not exceed 50. That's what this always is. Because if there are, say, 15 primes up to 50, there they are. And what they are P1 through P15. So you're selecting out P15, the last one. So this number, no matter what this number is, so instead of 50 you could put in anything, this will always be the largest prime that does not exceed a given number. So that's going to be 47. And that will eventually show up, because I'm going to write in it. All right, so we'd like to test for primality. So if m is fairly small, like less than 100, you can do a sieve, and not only can you tell if m is prime, but you can get all the primes up to m this way, very quickly. But if m is larger than this sieve is just, it gives you too much information and takes too long. Maybe we just want to target m itself, and we want to find out, is this m prime or not? So there are lots of straightforward methods for doing this. You could run through all the integers from 2 to m minus 1 and just check if each one divides m. The way you check for divisibility is you run the division algorithm, and if the remainder is 0, that means it's divisible. So you can check for divisibility for all numbers between 2 and m minus 1. That's called the trial division method. And this method actually works pretty well for m going from m being too large for the sieve, but up to, say, in the millions or so. This actually works pretty well. Maybe by hand up through a couple thousand. But trial division easily works by computer up through n in the billions. There are some ways to improve the test. You don't have to try all of the numbers from 2 to n minus 1. In fact, it's enough to check divisibility by all the values k less than or equal to the square root of m, and that are prime. So you only have to test these. So why is that true? Well, it's basically the same reason as we did the sieve. The first number you cross off is the square of the number. So if you take an imaginary sieve that goes up through n, what you're doing is you're crossing off every number. If you get up to the square root of m, and you haven't crossed off m yet, it's going to be prime, because you know that once beyond that, the first number you're going to cross off is going to be bigger than m. So it's because of the sieve. All right, and then you're only crossing off because of prime numbers. So you only have to test the prime numbers up to the square root of m, and you don't have to go over. Another way of seeing that, and I'm going to erase the sieve now. It was like a giant tic-tac-toe game. If n is equal to some a and b, where a is bigger than 1 and b is bigger than 1. So if m is composite, well, m is also equal to the square root of m times the square root of m. So a times b is equal to the square root of m times the square root of m. So the two products are equal. But what that means is that one of these two can't exceed the square root of m, and the other one can't be any less. So let's suppose a is less than b. Just arrange them so that a is less than or equal to b. Then a can't be bigger than the square root of m. So the smaller of two divisors of m can't be any bigger than the square root of m. So if you go through all the divisors up through m, up through the square root of m, you're guaranteed to get one of those divisors if m is composite. Okay. So that's another reason to see you don't have to go past the square root of m. Plus, the smallest divisor of m has to be prime, because if it's not prime, you can get a smaller one. So you only have to test the prime numbers. Okay. So for example, is 127 prime? All right. So what's the square root of 127 roughly? It's 11 point something. Okay. So I lied. There are some real numbers here calculated. But it's less than or equal to 12. It's actually less than 12. So what numbers do I have to do for trial division? 2, 3, 5, 7, and 11. And that's it. And if none of those go in evenly, none of those go in exactly, then it's prime. So it's easy to check. None of these divides 127. So it's prime. Trial division. Okay. I don't think this is particularly interesting, but you might find interest in it. I shouldn't say that. That's kind of insulting. Every prime greater than 3. Now that I think about it. No, I will not test you on it. Every prime bigger than 3, so every prime except 2 and 3, is always greater than, it's always within one of a multiple of 6. So it's always in the form 6k plus or minus 1 for some integer k. And that's not hard to see.
That's crazy.
If you look at the integer, start with some multiple of k. Start with some multiple of 6. So 6 times k for some k. And look at the next number, 6k plus 1, 6k plus 2, 6k plus 3, 6k plus 4, and 6k plus 5, which is equal to, it's 1 less than the next multiple of 6. Okay. Well, this is certainly not prime because it's a multiple of 6. That could be prime. That's not prime because it's a multiple of 2. It's even. That can't be prime because it's a multiple of 3. And we're bigger than 2 and 3. That can't, it's even, it's a multiple of 2. That could be prime. So the only 2 possible primes in this list, and that's certainly not prime. That's the same thing. Then I get to the next multiple of 6, and I repeat the pattern. So the only 2 possible primes here are that one and that one. Okay. So this happens to be a prime. The converse is not true. So here's something that's 1 less than a multiple of 6, but it's not prime because it's divisible by 5. All right. So I'm not going to, I've already done it. All right, another important definition. So we say that 2 integers are coprime, or relatively prime, or prime to each other, if they have no common divisors other than 1 plus or minus 1. In other words, if they're GCD, if the greatest common divisor is just equal to 1. So they have no divisors in common other than 1 and minus 1. So notice that if a number A is bigger than 1, then A is prime just in the case that A is coprime with every integer between 0 and A. So there's no common divisors between 1 and A minus 1. Okay. So, for reasons which will appear later, we are interested in counting the number. How many B's are there between 1 and A that are coprime with A for general A? So A may not necessarily be prime. We like to count how many B's there are that are coprime with it. This function has a name. It's called it's Euler's Totient function. So if n is any positive integer, then phi of n is the number of positive integers up to n that are coprime with n. So here's an example. Here is a table with the first few values of n from 1 to 8, and here is the value of the totient function, phi function, Euler's phi function of n. So 1 is coprime with itself, so you have 1. For 2 is coprime with 1, and that's it. So there's only one number there. 3 is coprime with 2 numbers smaller than it. It's coprime with 1 and coprime with 2. So phi of 3 is equal to 2. 4, I've got 2 numbers coprime with 4 less than it, the odd numbers, 1 and 3. 5, all 4 numbers between 1 and 4 are coprime with 5. 6, I only have 2 numbers co-prime with 6. What are they? 1 and 5. Okay. All numbers less than 7 are co-prime with it, so I have 6 of those. And then there are only 4 numbers co-prime with 8. What are they? They're going to be the odd numbers. Right, 1, 3, 5, and 7. How about 9? What's phi of 9? So got 1. I always count 1. 2, not 3, but 4, 5, not 6. They have a common divisor of 3. 7, and 8. So I count 6. So phi of 9 is 6. How about 10? Yeah, 1, 3, 7, and 9. Okay, so that's 4 and so on. Okay. How about 11? 11 is prime. If the number is prime, then everything less than it is coprime. So it's always going to be 1 less. That's easy.
Is there any way you can dumb that down even more? Because I'm not understanding.
Sure.
Still.
Okay. Let's pick an example here. Let's pick 9. Okay. Let's write all the numbers from 1 to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Each number in this list is either coprime with 9 or it's not. We're counting how many there are that are coprime.
I don't understand what makes it something coprime.
Coprime just means no divisors in common. So the GCD is 1. So they don't have any common divisors bigger than 1.
Sure.
So the GCD of 1 and 9 is just 1. So this counts. Okay. What's the GCD of 2 and 9?
1.
Just 1. So this also counts. What's the GCD of 3 and 9?
3.
So that's bigger than 1. So this doesn't count. It's not coprime. GCD of 4 and 9 is 1. So this counts. GCD of 5 and 9? 1. So this also counts. GCD of 6 and 9?
3.
It's 3, which is bigger than 1, so this does not count. GCD of 7 and 9 is 1. GCD of 8 and 9? Also 1.
So to find Euler's deal, you have to take that number and compare the GCDs of every number less than it, counting up?
At this point, that's what we're doing, but there are faster ways of doing it.
Okay.
How about GCD of 9 with itself?
It's 9.
Is 9, so it's bigger than 1. So count the circles, there are 6 of them. That gives you that number. Okay. So this is the way to do it for small n. I mean, this is really actually the fastest way. If you're going to do it for 9, this is probably the fastest way. But we're going to get to prime factorizations in a minute. If you know the prime factorization of a number, even if it's really huge, that gives you a very fast way of just telling what the phi function is. All right. So here's an observation. If n is a positive integer, well, if n is prime, then the phi of n is always n minus 1 because all the numbers from 1 to n are going to be coprime with n except for n. So it's 1 through n minus 1. Those are all coprime. And so n is prime. If n is prime, then this is true. But the converse is also true. In other words, if this is true, then n has to be prime. Because if n is not prime, there's going to be some divisor of n in that list, and you're going to cross it off. So it's going to be less than n minus 1 left when you're done. So the converse is true as well. So n is prime if and only if this is true. Well, okay, so we still really haven't seen a use for this thing yet.
True.
I'm just introducing it, but we're going to use it later. Moving forward. So why are primes important? General discussion now. Well, they're kind of the building blocks of numbers. So Euclid's principle is as follows. Let's suppose a and b are integers, and p is prime. If p divides the product, then it has to divide either a or divide b. This is true for prime p. It's not. This will not be true if p is not prime. So so this is Euclid's principle. It says that basically you can't take a and b together and mix them up and pull out a prime that way that you could not have already pulled out of either a or b. So if p divides the product, it has to divide either one of the two factors. So this is Euclid's principle, and Euclid's principle, well, it's true if p is prime, but it's not true if p is not prime. So let's take an example. Can we find an example? P is not prime. Let's say 6, where p divides a product of two things, but it doesn't divide either a or b. Can you find an example there?
30.
30. So how do you write 30? 30 as what?
It'd be like 3 times 10.
3 times 10, sure. Okay, so 6 divides 30, because 6 times 5 is 30. If you write 30 as 3 times 10, well, 6 does not divide 3, and it doesn't divide 10 either. Great. Great. Good example. Okay? So primes are important because of this theorem, and this theorem only. Every integer, at least one, can be represented uniquely, apart from rearranging the terms, as a product of 0 or more primes. So every positive integer can be written uniquely as a product of prime numbers. And the only difference is that you can rearrange the factors, but you can always do that. So in some sense, every number contains like this mix of primes, a unique mix of primes, and no two numbers have exactly the same mix. And each number, there's only one collection of primes that multiply up to that number. That's called the fundamental theorem of arithmetic. It's also called the unique factorization theorem for the integers. It says that the integers are uniquely factorable into prime factors. Okay. I'm including 1 here. So all the primes are bigger than 1. 1 is still a product of primes. It's the product of 0 many primes. It's an empty product. Empty products are 1 by definition. So if you have a product of 0 things, if you're not multiplying any things together, the answer is always 1. That's just the way it is. Well, you can imagine a computer program that would take a list of numbers and multiply them. What would you do? You'd set a product equal to 1, and then you'd go through and multiply each number into the product. And then you return the product. Well, if the list is empty, you don't have any numbers to multiply in, you're just going to return the product. So that's it. All right, so primes are the basic building blocks of integers. So let's find the prime factorization of some numbers. So 5328, we've seen this number before. We did it in the GCD calculation. So let's look at the sidebar first. So here's how to get the prime factorization. You can try dividing, take the primes in increasing order, and try to divide each one in. And then if it's successful, then get the quotient, and then keep trying to divide primes into that. So 5328 is even, so you can divide it by 2, and the quotient is 2664. That's also even, so divide by 2 again. Keep doing this until you can't divide by 2 anymore. So you get 1332, divided by 2, you get 666. Divided by 2, you get 333. This is now odd, so you can't use 2 anymore, so you go to the next prime up. You go to 3, and see if 3 works. So does 3 go into this?
Yes.
Yeah. And the quotient is 111. Does 3 go into that?
Yes.
Yes. The quotient is 37. Now, 3 does not go into 37, so try the next prime, 5. Does that go into 37? No. Next one, 7. No. 11. No. In fact, 37 is prime. So you're not going to find anything until you get to 37 itself, and then you divide 37 by 37, and you're left with 1, and you stop. And then the prime factorization of the number is just the list of primes you wrote down on the left side of the line. Okay. So that's a quick brute force way of getting the prime factorization of numbers that are not too large. So we can write this. We will group primes that are equal to each other. We can group them as exponential. So this is, we have 4 2's here, so we'll write that as 2 to the 4th. And then we have 2 3, so that's 3 squared, and then times 37. So in general, this is how we will write prime factorizations. We'll take distinct primes, raise them to powers, and then multiply them together. Okay. Questions on prime factorization? Every number has a unique representation this way. So, once we know the prime factorization of a number, there's lots of questions we can answer quickly. One of the things we'll answer, and we'll show you how to do this. If you know the prime factorization of a number, it's very easy to compute Euler's phi function, the totient function, the number of things co-prime with it. So I'll give you that formula shortly. But here's another question we can answer quickly. How many positive divisors does this number have? Now, if this might seem like the only way to do it is to run through all the numbers and then check to see if it's a divisor and then count them up. But if you know the prime factorization, there's a much faster way of computing this. So every positive divisor of this. So here's the thing about divisors. If A divides B, well, A is going to have some prime factorization, right? It's going to be, let's say, Q1 to the E1, up to Qn to the En. All right. So the Q's are primes and the E's are exponents. And this is going to have a prime factorization, S1 to the, well, I got to use another letter here, F1 up through S, and to the Fn. Okay, the S's are primes, and the F's are exponents. If this number divides that number, then that means there's some K, such that AK is equal to B. That's what divisibility means, right? Well, what's the prime factorization of that going to look like? It's going to include all these primes that are factors of A, and then some. Whatever primes that factor K are going to be thrown in there into the bag. So what that means is that the prime factorization of B is equal to the prime factorization of that. So all of these S's and all of the F's have to include all of these. So think of this as just a bag of primes. That bag of primes is going to be part of that bag. So all the primes here are also represented over here, possibly with bigger exponents. That has to be true. So in fact, all the divisors of 5328 have to be of this form. You include some collection of these primes, include some primes, but maybe not others. So it has to be of the form 2 to the A times 3 to the B times 37 to the C, where A can't be bigger than 4, B can't be bigger than 2, and C can't be bigger than 1. So they get be 0. But all possible combinations of those exponents will give you divisors. So this is just what I was saying on the board. So the only possible, if D divides 5328, the only possible prime factors of D are going to be among these, and the exponents can't exceed those above. So here's what we do. We count how many possibilities there are. So to do that, we just see how many combinations of A, B, and C are possible subject to these constraints. Well, how many values of A can there be? 5, because you include 0. How many possibilities of B can there be? 3. And how many possibilities of C? 2. Okay. So for every choice of A, for any of the 5 choices of A, you have 3 choices for B. So the number of choices combined for A and B is 5 times 3 is 15. Now for any of the 15 choices of A and B, you've got 2 choices for C. So the total number of choices for A, B, and C is going to be 15 times 2, or 30. So this number has 30 positive divisors. And you get all 30 of them just by taking all the triples of A, B, and C, such that A is between 0 and 4, B is between 0 and 2, and C is between 0 and 1. So 1, the number 1 itself is included in this list. How do you get 1?
Set all of them to 0.
Yeah, you set all the exponents to 0. That's one of the combinations, and that will give you, that unique combination will give you 1. Okay, so in principle you could actually write down all of these. But if you just wanted to find how many there are, that's how many there are. So this works in general. You take the prime factorization, take each exponent plus 1, and then multiply those together. And that's how many factors you have. That's kind of neat, I guess. You can do that. It's quick. All right, let's do this again for, not for 5328, let's do this for 6300, just for practice. So first we find the prime factorization of 6300. So we take 6300 and we divide by 2 and keep dividing by, whoa, I did a shortcut here. Here's the shortcut. If there are zeros, trailing zeros, these are factors of 10. So you can, 10 is 2 times 5. So you can pull out the factor of 10 right away. So you do this twice, and you divide by 10 twice, and that gives you simultaneously two 2's and 2 5's in the prime factorization. So that's kind of nice. So if you have trailing zeros, just take them off right away. And then what's left is 63, and now you go through the usual, but now you've, so you start with 2. If this happened to be even, you would start with 2, but it's odd, so we have to start with 3. Does 3 go into 63? Yeah. Goes in 21 times. Does 3 go into 21? Yes. Goes in 7 times. 7 is prime, so we can skip 5 and go straight to 7 and get 1. So the prime factorization of 6300 is what? 2 squared
3 squared
times 3 squared times 5 squared times 7. 7 to the first. There we go. Good. How many positive divisors does 6300 have?
84.
54. 54. Okay. So what do I multiply? 3 times 3 times 3, that's 27, times 2, that's 54. Same rules apply, so we don't have to repeat this rule. Okay. All right. So we already found the GCD of these two numbers. What was it? You remember? 36. Okay. All right. The GCD of two numbers can also be found from the prime factorizations in a very easy way. So any divisor of this is going to be, it's going to be 2 to the A, 3 to the B, 37 to the C, right? That's all the divisors of 5328. All the divisors of 6300, well, okay. So A here has to be between 0 and 4, B 0 to 2, C 0 and 1. So those are all the divisors of 5328. 6300, all the divisors have to be of this form, where now A is between 0 and 2, and so forth. So satisfy these constraints. So if you have a number which is a common divisor, which occurs on both of these lists, what does it have to satisfy? What's the exponent on 2? It can't be any bigger than 2. Right? This says it can't be any bigger than 4, but this says it can't be any bigger than 2. So it's got to satisfy both of those. It can't be any bigger than 2. How about the exponent on 3? 2. Right? It's at most 2. How about the exponent on, what else is it? 5? 0. Right, it has to be 0, because even though here it can't be any bigger than 2, there's no 5 in this list. Or you can think of it as 5 to the 0. So there's like a phantom 5 to the 0 sitting there. And so the exponent can't be any bigger than 0. What else? 7.
0.
Can't be any bigger than 0. How about 37? 0. Okay. So a prime, if you're going to have a common divisor, its prime factorization can only consist of primes that are common to the two lists. And then the exponents are going to be up to the minimum of the two corresponding exponents of the two lists. So that is the rule for a common divisor. So common divisor has to have this form. So all of those have to be 0. So it's going to be 2 to the A, 3 to the B, where A satisfies the whatever constraint is stronger. It's this one. A can't be bigger than 2, and B can't be bigger than 2. So
For the GCD, is it ever going to actually be less than the largest common value?
Nope, it's the...
It has less than or equal to, whatever one is.
These are so all the common divisors satisfy this, less than or equal to. But now the greatest one is the one where you satisfy these constraints, but you make A and B as big as you can. Okay. So in this case, the biggest common divisor is by making A and B as large as possible. So you're going to make A equal to 2 and B equal to 2. And that gives you 4 times 9, and that gives you 36. Okay. All right. Here's how I like to think. I like to think of each number as sort of being like a set of primes, but with repetitions. So in computer science, we call this a bag, not instead of a set, or a multi-set. So it's a bag of primes. So every number has its own unique bag of primes. Okay, so here are the primes. There's a 2. So for 5328, you're going to have 4 2s. So there's a 2, there's a 2, there's a 2. Okay, so you get this bag of primes. So this is A. And B, you get another bag of primes that might overlap with this bag. So you might see that there's stuff in common. The GCD is going to be the stuff in the intersection. And what's left over on each side is everything on this side and everything on this side are going to be different from each other. So P has to be different from Q. For any P in this side, any Q in this side. Because if they were equal, you would put them in the common intersection. So the GCD is the biggest intersection you can get by overlapping. It's the biggest overlap of the bags you can find. And when you get that biggest overlap, what's left over here are made up of primes, and these are also made up of primes, and no prime over here matches a prime over here. So what can you say if you take this is going to be another number. If you just take those primes, it's going to be, I don't know, let's call it X. And this number is going to be Y.
They have no common conclusion.
Yes, X and Y are coprime. They have no common factors. They have no common prime factors, so they have to have no common factors. So X and Y are coprime. Let's call this inner thing, let's call it G. G for GCD. So here's what we know. We know that we know that A is equal to X times G. Because here's X and here's B, you're multiplying that all together, and that gives you A. And then B is equal to Y times G. And I know that GCD of X and Y is equal to 1. And the thing is, this constraint and this constraint uniquely determine all three numbers, X, Y, and G. Okay, there's only one G that can give you, there's only one G, one X, and one Y that gives you all of this at the same time. And that's the greatest common divisor. All right, so I like Venn diagrams. So we've seen Venn diagrams a couple different places. So what if you take the union of this?
At least
Yeah, so if you take everything in here, and then everything in here, and then everything in here, that's going to be X times G times Y. That's the least common multiple. That's the least common multiple of A and B. Right? It contains everything in A, so it's a multiple of A. And it contains everything in B, it's a multiple of B. And in fact, you can't get any smaller multiple. So anything contained in this bag has to be in this bag, and it has to be in this bag together. And the smallest way you can get that is when you get the biggest overlap of the two bags. So notice this number, of course, is less than or equal to AB. But, so what is it, actually? Well, this is equal to X, G, Y, G divided by G, right? I'm just multiplying by G over G. But that's A, and that's B. So this is AB over G. So the least common multiple is actually take the product, divide by the GCD. Because the product, when you take the product in the Venn diagram, if you look at the Venn diagram, when you take the product of this bag, and then you take the product of this bag, but then what are you doing? You're double counting the intersection. So you divide by the intersection to go back to a single count of the intersection. So that's why that's true. So, questions on that? Oh, it's past break time. Oh, yeah. Let's take them.
That's a witchcraft. No.
Oh, we
No.
We should go to the bathroom or something. God. You know, figuring out.
I have one at the house. I just haven't played with it.
Super cool.
Yeah.
That is insane. What's that? That is.
That's witchcraft in your pocket.
I totally know that it's not
Skipping through.